Good evening. Tonight I have the distinct pleasure of introducing to you Steve Stokowski. He's the owner and materials geologist for Stone Products Consultants. Louder. Okay, and he will be presenting on petrography, which is the analysis of weathered materials, microscopic analysis. He has a Master of Science degree in geology from South Dakota School of Mines and Technology, and he's been involved with many of the restorations in Washington, D.C., the Iwo Jima Memorial, World War II Memorial, and several others. But anyway, I give you Steve.
Thank you. Now, when there's text up here, I usually won't read it to you because you can read faster than I can speak. But I got lots of pretty pictures, and petrography isn't taking pictures of your pets. But we have lots of things here. Now I'm going to usually start off with just some pretty pictures, and then we'll go into the meat of the talk. So let's start. So now what does all that stuff mean? Why would you work on a building and do a microscopic analysis before you do a repair, or after there's a failure and you're looking at some forensic issue, or for rehabbing it, or for any of the other normal engineering reasons for looking at buildings and structures, particularly historic structures? The kind of methods that I use primarily are microscopy, but within petrography you can use whatever you need to use, chemical analysis, physical analysis, anything like that.
Can you define petrography, please?
Sure, we're going to get that.
Okay.
Actually, like 2 more slides. And with petrography, you can determine the components of historic materials: concrete, stone, mortar, terracotta, anything of that nature. And I'm also going to go through all that, and then there's going to be a number of example projects, and we're going to keep continuing on. So at any rate, I told you what to do, why we do this in the beginning, and it's actually why civil engineers and structural engineers or architects are involved in the process, and usually they're the ones that have the job up front. Here's the definition from one of the old hands in petrography, a guy named Richard C. Mylans. So you can use all sorts of things, and just if you find a petrographer out there and he isn't carrying a hand lens around, he's not much of a petrographer in my mind. So you need to have a knowledge of all kinds of materials, not just rocks and minerals as a geologist, but all historic materials that you might come across, gypsum, concrete. How often do you see that or use that now? Not at all. I've looked at concrete with wood in it, not accidental wood, but sawdust, plasters with wood, materials with perlite in them. But old style perlite, before they understood that there was a difference between structural perlite and insulation perlite, and they had used insulation grade perlite in the floor of a building in World War II to correct a mistake that was made. So guess what? They don't make it like they used to because they failed then and they had to fix problems, etc. One thing you can find online, and here's a lot of gobbledygook because it's from the government, you can find a manual, petrographic methods for examining hardened concrete. And that's mostly for modern construction, but there's a couple mentions of stuff for historic construction in there. Here's some of the tools that are used: a microscope, hand lenses. Now we've got digital cameras and computer screens. A thin section. What's a thin section? It's a thin slice of your material, and it's usually around 30 microns, which is the thickness of a human hair. Most materials that appear to be opaque aren't opaque at all. And if you keep a constant thickness and a standard thickness, you can rapidly identify what you're looking at. But because of the optical properties, you can also identify things from their texture. There's a lot of different types of microscopic techniques that you can use. Most petrographers are using polarized light, which is often abbreviated as PLM. That's an acronym. I don't like to use it because people's eyes glaze over when you start talking with too many acronyms. You can use a scanning electron microscope with backscattered electrons, energy dispersion analysis, identifying the chemistry in detail at a microscopic level. There's a standard way. There's a lot of ASTM standards which will define how you should do some things, and other ones which are guidelines, and they're often in error. But this is old school stuff. This is a modified metal lathe down here just to scan your specimen back and forth. And here's another type of hand cranked one. And here's a more modern device which is computer controlled. And why would you do that? To get proportions. Of course, everything is designed with essentially volumes, but if you put a slice through a material, you get an accurate sample unless it's completely segregated, and you can determine the volumes of materials off of it. Now, most of what this has done is to determine the air content in concrete, and the air is essential, particularly in more northerly climes than in Atlanta, for freeze-thaw resistance. There's nothing that's as effective at the price other than air entrainment for giving freeze-thaw resistance to concrete. But a lot of this talk has to do with historic dimension stone, and there's lots of different types of materials there, and there's some things that historically granites are defined by geologists as something with 20. It contains feldspar and a sodium or potassium aluminous silicate plus quartz plus a couple of other minerals. But the quartz has got to be 25% or more. And historically, the granites for dimension stone had a lot of feldspar in them, and they were medium to coarse grain, and that's because they're easier to work that way with a hammer. You could split these things. If you get a fine grain granite, it's hard to work. Occasionally there's gneisses, and gneisses may have that composition, but they'll be layered. And they give a big problem for dimension stone because they're hard to split properly. Black granites aren't granites at all. They don't even contain quartz. And it's usually a rock type called an anorthosite. Sandstones are used. There's a whole type of rock out there called brownstones used for buildings, but there are a variety of sandstone. And there's other colors too. Marbles. People like all white marble or black variegated marbles, or a marble type which isn't really composed of the mineral calcite or dolomite is vert antique, which is a serpentine.
What kind of granite do we have around here?
Around here, mostly we've got a lot of slightly weathered granites. They're not necessarily, except for out by Sparta, there weren't very many alkalic granites around here, and a lot of them have foliation and nice exfoliation in them for the dimension stone part. But they just about all, except for up in northeastern Georgia, their primary product line is crushed stone. and not a dimension stone, which are blocks of material, either sawn or split. There's other types of things that you see as dimension stone, just pieces of quartz. And there's cast stone, which is a concrete type product, but it's often, historical architects, they're going to be talking about cast stone and dimension stone. And these were blocks made from concrete, a couple different processes, and they usually have great control on the aggregate color and size ranges, and they make them into blocks, and then they were laid up as masonry blocks as opposed to cast in place concrete. So it's a different product. Here's an example of one, and can we get the lights maybe a little bit? Is there a way to do that?
Sorry.
No? Well, this is the Manhattan Bridge in New York. As you might imagine, it goes into Manhattan. It's got these carved, this is all stone, and here's some carved sculptures on it. And some of the sculptures have little depressions in them, and they're showing up when you see these depressions as brown and red spots. But there's actually two kinds. My goal, my task from a historic architect was what's going on with this sculpture? Why is it discolored like this? We can clean some of it off, but we can't clean all of it off. Well, the problem is that this is the original surface. It's weathered down, and the feldspar was partially altered to an iron hydroxide mineral, and you see more of it when the pieces have popped off. But in addition, this particular sculpture has got weld splatter and grinding splatter on it from when they were working on the adjacent bridge. So when they did the revisions, they did not have great control of their dust and their splatter from welding, and it got all over this sculpture, and that caused problems with it. So they could clean this off. This can't be cleaned off. Historic brick, we're going to change it to another type of material, brick and terracotta. These are products made from clay, but they're not clay. They've been fired so that the clay's been altered to moldite, and some of the other minerals have melted to form glass inside the material. They have a lot of different colors. People think of brick usually as red, but there can be many other colors to it. They have, depending on their manufacturing quality and type, they can have good freeze-thaw resistance, or they can pass this ASTM test on freeze-thaw resistance, but still fail if you had this product that is extruded out and had variable pressure coming out of the extruder, and you get voids, long strings of bubbles, which will speak well for the people who are old enough here, most of us I guess. Remember Coke bottles, the Coke bottle type of shape? Well, those bubbles get the Coke bottle shape, and at the throat, ice will form, and it'll be melted inside the rest of it, and then when the rest of that freezes, the brick will burst, or the terracotta will burst. There's different types of weathering, internal chemical weathering, or cracking from the mortar. If the mortar changes volume, it will crack the brick because of the mortar changes in volume around it. It'll push the faces off sometimes. Here's a bunch of bridges. These are bridges in Boston, and in this area we have Olmsted, who was the main landscape architect, and he did some of the parks, linear parks in Atlanta, that was his last project before the man died, and they're in what is that, Decatur, I guess, and so. But these are in the Boston area, and they're part of the Emerald Necklace. And these are made with stone and also with brick, and different kinds of brick. And the brick that was failing was brick that was extruded and had this Coke bottle arrangement of bubbles in it. So it would pass the test, but not pass the real requirement of surviving in nature. In addition, there's a type of deterioration mechanism in concrete that involves the aggregate and the cement, and just about all rocks are not stable in the presence of high pH that you get from the main product of cement hydration, which is calcium hydroxide, hydrated lime. And you almost never see this with mortar, but it had ASR in the mortar too, so that was causing the mortar to slightly expand and leading to a secondary failure mode in these bridges.
What was the fix?
What was the fix? You had to take a lot of it out and put a siloxane on it to keep it weatherproof. But these bridges were failing underneath, and a big part of the problem was that they were backfilled with dirt. I wouldn't call it aggregate, I'd call it dirt, and they were leaking a lot from the top, so they needed to have a way to seal the water off the top and have it run off of the bridge and not just soak through it and get down into the brick and saturate the brick. Historic concrete. Concrete is not just something that's gray. It's had a long history of different products that were used as the binder and different aggregate sizes through the years. Portland cement really, even though it was invented in 1823, it didn't come into the United States until it came into Copley, Pennsylvania in 1873. And it wasn't used widespread until about 1890, and then more so afterwards. And before that, there's a type of product, and it lasted longer, called natural cement. And it's a different type of cement. It is not Portland cement at all. And there was also slag cement. And there was slag cement produced over in Birmingham. There was a lot of slag cement produced around. But they did not understand the technology of what they were making, the chemistry or the minerals or anything. And in the 1920s and 1930s, the Portland Cement Association essentially put the slag cement producers out of business. And they didn't come back online until 1980, 85 or so in Baltimore, where a German company came in and started to produce material there. In historic concrete, you have natural gravel. You also have crushed stone, although they didn't have the kind of crushers we have nowadays. And they often use really larger type of aggregate, 1.5 inches. And you don't see that much except for road construction nowadays. You can also have large blocks, plums, they call them plums. They would just put a piece of stone in your massive concrete structure, and it would take up space. And then if you core through that, you wonder what's going on later during the investigation. But it's...
What was the kind of concrete product that the Romans used? They used...
I have a hard time hearing you because I'm deaf like this gentleman here.
The Romans used.
What was the Roman time concrete?
The Roman concrete was a mixture of hydrated lime and volcanic ash, glassy volcanic ash. And the glaciest material was around Mount Vesuvius, but there's other sources of volcanic ash around, and they were not as good because they often did not have the high glass content, or they had a mineral called zeolites in them, which would then lead to degradation. But I'm not a big fan personally of the statement that, well, this Roman concrete is something that has lost great technology. We're seeing the relics that survived at 2,000 years. Everything else that did survive, we don't see. And I've looked at some of the concrete. There was concrete that I looked at in from Germany, and mineral types in the rock that I know the ASTM people who are involved with ASTM C9, which is the aggregates part, they are horrified when I mention that there is reactions with some of these other minerals because they don't have to contend with that now. But what does it matter? The concrete was 2,000 years old. There's no design. Even somebody dreaming that they're going to design concrete for 2,000 years, they're not. They might design it for 150 years, even if they say 300 or 400 or 500, definitely not 2,000. So those long-term reactions, the structure is going to have outlived its usefulness and will be just an artifact. But that old concrete that the Romans built that survived because it had some other protection, maybe it was on land and then later was immersed in the sea, or it had some other things around it, is not the typical concrete that was made by the Romans. And they didn't make it deliberately and with purpose to survive for 2,000 years. They just made it. And hey, wound up working. They're great. Let's go on here so that we don't run out of time. Here's some bridges. These are Art Deco bridges, and this is the Highway of the Future in Connecticut. And these are beautiful structures. This was built in the 30s. And here's some of the features you can see in that concrete. And it's hard to see because we can't get the lights out, but in any event, they have a natural sand in there, and what's important about the sand is that it doesn't have red sandstone in it. It's got schist in it, mica schist, and it has this coarse cement, which brings it down to the age of what goes the older cements used in concrete were coarser. So you have particles in there of cement that are 3 millimeters sometimes across, and now you're hard pressed to see particles of cement that are 100 microns across. And it has this very strange texture in the trap rock, which is a basalt in there. And we'll go into that more. And the company, one of the companies that was a big deal at the time was New Haven Trap Rock. And New Haven Trap Rock is like an historic great company like Davison Mineral was in Atlanta, and more so. But this particular, I think I'm losing some slides here for some reason. I don't know.
The page count at the bottom is incrementing.
Well, we'll just go on. Mortar, here, I got to elaborate some more. Mortar is typically, they have fine sand, and this is the far end of a delta where you get that fine sand. It's not river sand, which has got coarser material in it. And you can tell different where the sources are from the rock particles or coatings and things like that. The binders in mortar have hydrated lime in them, and occasionally some other things in there too. And pigments too. But it's hard to match a lot of this stuff because these pigments, old pigments, are coarse grained. So you can just identify the kind of pigment that's in there, but to replicate it nowadays, you have to do lab work so you get the correct color. Here's an example from over in Alabama for a mortar. This is mortar that was made in one of 3 time frames here for this particular building, which is part of their museum. And we got fragments of this, and you can identify things in there, the amount of air, this blue spots here, that's blue dyed epoxy, which has filled up the air voids, and with mortar and cement in concrete, the air voids are in there for mainly freeze-thaw resistance, but in mortar, they're mainly in there to make the material more workable, so it's easier to lay up the bricks. And they would put tallow in the mortar. I think they probably put tallow in this stuff. There's big particles here of hydrated lime, so they didn't mill it down. This was a locally produced product. These guys might have produced it right on site there. And there's this type of the green spots where you can't see up close here, but it had this very unusual cement addition to it to make it develop a relatively early strength. And that cement has got particles in there which are rich in iron and reduced iron, and that turns them into blue. So I think that what that came from was that it came from Birmingham or up there, and they were actually making cement using ground up ACBF, air cooled blast furnace slag, as a feed into the cement plant, but they weren't completely melting it, because some of it is partially melted, but they could have even been feeding it in solid particles in the end to adulterate it. But that is present in this mortar. In addition, I found this one particle across here, is this fiber. Turns out that's a cotton fiber. It's not important to my report, but I think that this cement came with in cotton sacks, which I thought was kind of a cool little side thing. Okay, here's into part of the main examples here. This was an emergency. It was called by a superintendent in the Park Service, and he wanted to match an aggregate because they were going to do a repair on the Iwo Jima Memorial, which is in Virginia. It's actually called the U.S. Marine Corps War Memorial. It was built in 1955, and I was doing this in 2004, and they needed to repair it because they hadn't done any maintenance since 1955. And the architect of the Capitol said, "Oh, that material." Now here's where it is. That material, which is actually in front of this concrete, exposed aggregate concrete, is Swedish black, and you have to get on a Learjet and go to Sweden and bring some back in 55-gallon drums now. Well, he hired me instead. But here's some pictures of the actual Rosenthal picture from Iwo Jima and the memorial as it's translated into bronze. But what we're actually working are these parts around here, and that's exposed aggregate concrete, and it's black, and it's formed and it's skid resistant, so you're not going to fall on your head, and the millions of other people who have visited this are not going to fall on their head, and they're not going to wear it out because they used very high quality concrete from a locally at least well-known precaster, John Joseph Early. There are people I think have shrines to Early. This is what the material looks like close. It's a black fine-grained rock, and in between it, this stuff is relatively small size, 3/8 of an inch. In between, it's got little smaller sand particles. They're bottom ash. That's the molten material that comes out of burning coal, and it's collected at the bottom. And that's been crushed, and that's been used extensively for sandblasting grit. And in this case, he was using it as this decorative aggregate in this concrete so that the concrete would be black. If you look at the rock in thin section, it's not black, it's translucent. And if you use the petrographic microscope, you can get these nice pretty colors, which are great for presentations. But without putting that part of the microscope in play, the material is just transparent. But what can you see from this? You can see that it has feldspars and it has amphiboles in it, and it has a fine grain size which you can measure. Why is that important? That's important because there are historic quarries all down here around the DC area, and this is where the actual monument is. And without more in-depth knowledge, you could say it could come from any one of those quarries, and for the most part, you'd be completely wrong, because these quarries are producing coarser grain diabases in there. But Leesburg is on the north end of that, and at the north end of that, the quarry that was in operation at the time was operated by the Arlington Crushed Stone Company. Arlington is 30 miles away from Leesburg. But, so people were confused. They thought, well, Arlington and Crestone, where were the quarries? Over there. They didn't operate over there. They operated over in Leesburg. And they operated this one quarry, which is now a water supply going into Northern Virginia. But this quarry here, and the rock in this quarry was a bunch of small dikes. So we're talking about volcanic intrusions of diabase into the surrounding rock that they're about this thick or this thick, and they chilled very quickly and made fine grain size. All the other quarries are in structures that are called laccoliths, which are big. They may be 300, 500 feet high and a mile or so wide, and the rock cooled slower when it was molten and the grain coarser grained. So they came right from this quarry. And if you wanted to match that with the grain size, you have to go to that quarry and produce a little bit out. Now, at the time when they're doing this repair, they can find that. But now it's flooded. You have to go somewhere else. Here's another one. The crumbling loggia. Who here knows what a loggia is? Good. I didn't know what a loggia was either before I did this project. This is at the Oak Ames Memorial Hall. Anybody recognize the name Ames?
Their department store.
Shovels. Shovels. Location of this is south of Boston in northeastern Massachusetts. And Ames, there's the building, which you can't see at all because of the light. But a loggia is essentially a porch that's enclosed underneath the main part of the structure. So it's like a room that has openings into it, and you walk into it, and it isn't a screen porch or anything like that, and it's part of the structure. So the walls go down and they're transferred the load to the ground with columns, and you go in that way, and then there often can be a couple doors or windows. You go in there. This particular structure, and I'm really disappointed that we don't have the ability to turn these lights off, but it's got a different rock type and sandstone on it. But it's an historic structure with crumbling brown stone. And the Ames name is a big deal. Ames was a blacksmith before the Civil War. He made shovels. He was the friend of Abraham Lincoln, and he got the whole shovel concession for the Union Army. They made money hand over fist. He had so much political power. His sons, Oaks is one of them, became congressmen. And then Oaks, even though we got this nice structure there, he became a congressman who was involved with the UP Railroad and the UP scandal during the construction of the Transcontinental Railroad. And he eventually was run out of office, even though he was a powerful, extremely wealthy man. And there was a TV show which is called Hell on Wheels, which is part of it. Oak Ames is part of the TV show, but he's got a structure here built to memorialize him, and there's a park up there for Ames and all that. And in the middle of Wyoming, near where the UP originally went across, there's a pyramid built with local rock, the Oaks Ames there. But at any rate, so that's some of the back history, and here's this historic structure, and the brownstone on it is deteriorating. Well, here's where it's deteriorating on the outside, and you can see a little white line here. You'll see that closer in another part of the column. And this brownstone is from central Massachusetts, and it's the Longmeadow sandstone. The Longmeadow area there, people want to match this all the time, but it's got residential development on top of it now, so you can't do that. The granite was locally sourced, and that quarry, you could open it again, but you don't need to because it's very durable. Here's where all multicolored, you can see this fairly well, and this stuff is scaling off. On the interior, on some of the columns, it has these great carvings. This guy's got owl and chestnut oak leaves and acorns carved into this. And on the inside of this loggia, the sandstone is deteriorating. It's crumbling away. Out here, it's got a white deposit on it, and it's nice and sharp. The carving is nice and sharp. Well, it's a different material on either end. So outside here, it's gypsum, and the gypsum has actually cemented the sandstone together. Inside here, it's a mineral called mirabolite and phenerdite, depending on the hydration. I'll go through that a little later. And it's causing this sandstone to disintegrate on the inside. Now, the original plan was to take this area on the inside and heat it up, and that would deal with the problem. But that was when they were mistaken what the problem was. They thought that it was freezing and thawing on the inside. But why would it freeze and thaw on the inside and not on the outside where it gets wet? That's because it had this mineral, this salt forming in it, and that was causing the disintegration. On the inside, it had the same kind of thing. There's a little bit of graffiti, and it's coming off in sheets because this is a different type of sandstone that is more suitable for blocks and not for carvings. Mirabolite is a sodium sulfate. Phenerdite is a sodium sulfate, and it's not hydrated. This material is used in ASTM C88, and it's been used for close to 100 years to determine the durability of rock. Why does that work? Because this material changes phase with slight amounts of temperature and humidity. This is the normal range that you see. Man, it is cycling through a couple times a day. You have to have material that's very, very durable to survive this, particularly over the lifetime of a structure, not just the 10 cycles in the test or the 20 cycles in the test. So it goes back and forth between mirabolite and phenerdite, and it'll form efflorescence, and it'll do it with heat, and it'll do it with humidity. This is what the stuff looks like when you extract a little bit of it and cause it to crystallize slowly underneath the glass slide. And in cross nickels, these are cross polarized within a petrographic scope. It's very colorful and pretty. If you dry it out, it's not pretty at all. If you take the same dried thing and you take your microscope slide, which has got a cover slip on it, mind you, so it's not hard to get, it's very hard to get moisture in there. Just go, breathe in it. You can hydrate the edge of these crystals, which are dehydrated. Right there, that's how fast it'll hydrate. And that's what it'll do for rock. And that's what was happening here. Where did the sodium and where did the sulfate come from? Well, the sandstone has the relic of a mineral pyrite in it, which is iron sulfide. These are these cubes which are converted through weathering to iron hydroxide in there, and that's where the sulfate comes from. Sodium is just everywhere in the world. It is everywhere, so you can have a lot of that in there. Now, where did the calcium come from? Is it coming from the mortar? Well, actually, it can come from the stone itself. Here, this has got a feature. This is the mineral calcite, which is calcium carbonate, and it's got a feature in the petrographic microscope, which is called birefringence, high birefringence, and that's what this is. That's calcite. So you can identify this pretty quickly. In addition, on the inside of the building, they were putting calcium chloride down, which, as you may remember, absorbs moisture from the air, and that was something that was accelerating the deterioration because they needed to de-ice it, and they were putting calcium chloride down. They didn't need to put calcium chloride down. They would have been almost better off putting sodium chloride down, but they still would have had deterioration and maybe just not as fast a rate. Here's the formula for calcium chloride when it's fully hydrated. And here's what it looks like when you precipitate it out under in a slide. So it makes these nice little, very diagnostic crystals, which lead to great photomicrographs that then you can use in a presentation 20 years later. Bricks and immigrants. There's the immigrant photographer for the New York Port of Entry was John Jacob Reese. And there's a park there on the edge of Long Island, which is called the Jacob Reese Park. Gateway National Park is what it's called now. Here's where it's located. For what it's worth, this is Sandy Hook right there, where the hurricane came in and destroyed lots of things all over in here. And this is Long Island, a portion of New York State which wants to break off as its own country, or its own state, not actually country. But here's this particular building at the time of construction in 1936. This is a bathhouse, and Reese actually had his facilities back in here somewhere. And you can see this brick has got a lot of multicolors on it, and it's mostly red, and it's got a lot of white stuff in there, which is another type of brick in there. And when you work with any kind of building or material from the Depression era, you have two types of quality: amazing or poor. Poor. And I think that you can make up your own mind of why some are amazing and why some are poor. This one was poor. They had problems with, here's where it's located, it's right on the water. You get sea breezes coming in, salt spray. I mean, you're on the ocean, you got ocean here. Salt spray's going another half mile inland. Here's another illustration of the end of the building. You can see it a little better. And here's a picture from 1936 with people in period clothes, not just reenactors, straw hats. And here's, you can see a lot of the cracks that were happening early on, right about the time of construction. The Park Service is going to keep this structure, but bricks fallen. The bricks cracked internally. What are they going to do about it? Here are the preservation efforts. Right after construction, they painted it and they put something on it called a protective coating, which apparently wasn't paint. I have no idea what it is, and nobody can find out. Then they put it in during the war, they put waterproofing on it because this wasn't working. After the war, they coated it with tar, put mastic on it, and because it was really deteriorating, so everything was stuck together and didn't fall off the building. Then the Park Service acquired it in the early 60s, and they sandblasted the surface and they put silicone on it. Now, silicone and siloxane are different, and silicone is actually the lesser material that you would want to use, but in 1963 it was totally cutting edge. So they shouldn't have put it on there, and they can't get it off. And then it's been falling apart since then. Here's what things look like. Mortar joints are standing out. The surface is degrading back on the brick. This is part of the interior. These spots are areas in the interior of the brick. Here's another little close up here. You can see that a little better. Perhaps you can see the way this is below the level of the mortar. The mortar is a very strong mortar. Shouldn't have been that strong, etc. Now here's the sample that we had, and here's some of the things you can see right off the top with the sample. It's got deposits between the mortar and the brick. Those are identified as gypsum calcium sulfate. Didn't know at the time where that came from. There's cracks along the edge of the brick and they go into the mortar. So the mortar isn't causing the brick to crack, but something happening within the brick is causing the mortar to crack. And if you saw the brick in half, you can see it's got these feature that it's reddish on the outside, and then it's lighter colored, and then it's black on the inside. It's got these long cracks in it, and it's not interesting. It's got these big bubbles kind of outside and not so much on the inside. And between the brick and the mortar, you often get a layer of gypsum forming because of reaction between something coming out of the brick and something in the mortar. If you look at those bubbles I pointed out to you, the gas bubbles have black minerals in it, which indicate that it's a reduced mineral and something that formed at the time the brick was fired. Well, what did they use? They used clay from the Sayreville, New Jersey brick pits. The Sayreville brick pits are really well known to people who are doing historical stuff. Plus, they're really well known to mineral collectors because that's where you go and get big crystals of pyrite and marcasite, both iron sulfides. You get them out of these pits. And this was the Depression. They were probably just scraping the bottom and taking any kind of stuff they had because they were not making money and making brick and selling it to the government to build this building in New York. And then the building almost immediately was starting to fail. So that's the low-end quality on the Depression era stuff. Here's a picture of one of the pyrite nodules that you can get out of the Sayreville brick pits. Very well known to mineral collectors.
How are you going to fix it?
How are you going to fix it? Well, fortunately, I'm not involved in design. I suggested to them that they needed to build a steel structure inside the building, and that be the actual building that they use, and the stuff on the outside just keep people away from it because those walls are going to come down. I don't think it's fixable, bottom line. Art Deco bridges. I mentioned stuff about the Merritt Parkway, Highway of the Future, the southwestern Connecticut. That's this red line going up here. This is the Connecticut River. This is the edge of New York. This is New York. These structures are beautiful. They have castings in there. This is an Indian. This is a Puritan. This here is one that's really deteriorated. They've all deteriorated because these are historic pictures and pictures from the time of construction. And here's civil engineers and surveyors working on building this, so everybody gets their image in these structures. And nothing really happens for 50 years, and they're deteriorating. And you can see here this little black stuff. The aggregate is becoming exposed on the surface because the surface of the concrete is weathering off. They need to match that. Not the way it looked like originally. They need to match what it looks like now. That is hard to do. That is hard to do because it's exposed aggregate concrete that wasn't designed to be exposed aggregate concrete. You have to reverse engineer this material to come up with the actual as-built concrete proportions. But we did that, and it's got crushed stone of basalt, and it has this unusual texture in it, which I did not at the time understand the significance of. Fine aggregate. The fine aggregate has rock types in the coarser part of the sand that indicates it came from southwestern Connecticut, as opposed to more towards the Connecticut River where you have red sandstone particles in it. The cement came from Pennsylvania. Most likely it's a buff cement. And they actually made this concrete with pretty good water cement ratios. Low, you determine the proportions, determine how it was weathered. There's no alkali silica reactivity, nor would you expect anything with basalt. But you might expect something with this metaquartzite, but nothing happened. And it was not air entrained. So the real question is where did the basalt come from? And there's two major possibilities, one of which are all these what are called sills going up Connecticut, and the other one is stuff that's closer actually to the location of the construction, which is over here. Now we were actually over here. Let's see, that sample was from right here. So there's a good reason to think it could have come from here, but that particular material over there does not contain this texture, and this texture forms in these big volcanic flows, basalt flows, where you have the relatively fast cooling at the top. So these crystals formed long crystals in there, and they formed a network, and actually the rock's pretty tough. But that's where they first started to quarry, and they're in quarry at the time that they were actually building this road. You go further down, and most of what they're producing now is more uniform texture, like down in here, very different and distinctive. They still have this. I found this online. This is the old locomotive that hauled this material around. So they laid a rail line going down along where they're going to build the highway, and they hauled stuff up and down there, and then they took it out when they were done. But the same locomotive has been restored and is in the museum there. And I know a lot about the New Haven Trap Rock Company because a fellow who I worked with at Vulcan had worked there back before the war, and somewhat after the war too. And it's a fascinating company. It doesn't operate now as New Haven Trap Rock, although most of the people up there will be talking about it. It's now Tilcon. And here's the last one here. Here's a classic thing, a high-rise icon in Georgia, in Atlanta, Peachtree Center, downtown Atlanta. The location, right in the center of Atlanta, Peachtree Center. This is what they look like, at least from the air, and this is what they look like from the ground. You'll recognize this not just by this rectangular windows, thousands of them, but these little sky bridges up there. They're a big deal when they put them in. I don't think they're so much of a big deal, but still around.
Tubes.
What's that?
The hamster tubes.
I can't, sorry.
Hamster tubes.
Hamster tubes.
Oh, yeah, hamster tubes. I guess you could call them that. But you know what? I think it's probably safer to walk across there than to walk across the street. Or maybe even to be on the street. I don't know. But the kind of sample I got was small. The piece on the edge of some of that concrete there. And it's got all this white exposed aggregate concrete. This is not exposed due to weathering. It's exposed by design. We sawed it in half, and it's got these brownish particles in there. But if you were to look real close here, this is weathered to be actual whitish clear and dirty now at the surface here. What is this? What value is this to you? Well, this could be, at least from the color, chert, which would indicate the source would be coming from Alabama or coming from the Tennessee River up in Chattanooga. But that isn't chert at all. But this is what the gravel looks like. You know, it's got a lot of, it's a high-end metamorphic rock that has a lot of sutured quartz in it, which indicates that it's very old. It's got some feldspar in it, but not much. The quartz is strained, and it's been subjected to pressure, but it's also been it's got a small amount of mica in it, and that could be relevant to you if you're looking to see whether there's a granite for the source rock that was then weathered through geologic time, made into pea gravel, or not. So you look a little closer, and this is the surface of these grains are really etched at the surface. So this has been a deposit that isn't just a local river deposit. This is something that's that's old, probably 20 million years old or something, maybe 40 million years old, that's been sitting there weathering. And it does not have the schists in it, which you would get if you were coming from what's the current main source of sand into Atlanta. This is Atlanta sand, although it's not in Atlanta. It's way down over here. But there's some schists and all that, which would come down into this particular material. So it isn't coming from Georgia at all. Where is this coming from? And this is a geologic map, and you can determine, what the rock types would have been supplying these sand pits, which are all along the edge here, going up. So I went to the Aggregates Manager, a reference book which is produced every year, and you can take it back into the 50s. And it has different pits and their current name. You can plot these on the map, but conveniently they've plotted for you. And you can look in Atlanta to see whether there's anything combining this with the geologic map. There's nothing else that I was unaware of. Nothing else in Georgia that I was unaware of. South Carolina, no. But there is something in North Carolina. And up here, if you were to look at the geology, you don't have these schists in there. You just have granitic rocks and quartzites that had weathered. And in fact, the pits are really right here. And there's a rail line which goes all the way up, goes up to here, and it comes down into Atlanta. Those particular precast panels were made in North Carolina and rail shipped to Atlanta. Imagine that, Atlanta being a rail hub, getting material from a couple states away. But that's where it came from. And we found the rock type produced there. They still produce it. And it has the same rock types as in the original material. And they didn't need a lot for doing the repairs. In fact, they only needed basically a pickup truck full. So they just drove to North Carolina, got a pickup truck full to get material, make the repairs, and to match exactly this aggregate. So that was a good thing. And like here, like I said, it came from here, went all the way over here, and came down along 85. The rail runs along 85 to Atlanta. Didn't come from here, came from up here.
How do you specify how to find that material from that yard?
Well, they had to hire me to find the material. I mean, that was part of what is this material, how can we match it?
Yeah,
And so the question is, first, what is it? Looking at what it is, where could that come from? Didn't come, I've done similar projects in the South, and the material has come from Chattanooga, but this didn't come from Chattanooga. It didn't come from Huntsville. There's a little bit of difference between the pea gravel from there, those two places, and it actually came from North Carolina, like I said. And I've been in North Carolina a lot, but I've never actually been to that pit. They did this all on the internet, and it matched exactly.
Wow.
So you had to do some detective work.
Absolutely.
And once it was decided what it was, how did you record it so that in the future they won't have to hire another one of you?
Something? I would like to be idealistic enough to think that my work is going to last for all time. But I'm not that idealistic, and they'll probably have to hire me again. Or they'll hire somebody else after I'm done, and they'll go through the same process, and maybe they'll screw up, and it won't match properly. Go ahead, sir.
You've given us a very fascinating presentation here tonight. My concern
He can't hear you, you want to talk up.
Yeah, I'm getting my hearing aids on Thursday, so right now I'm deaf.
But my concern is some of his. I'm just curious in your subjective opinions. You've spent 40, 50 years learning how to do this stuff. That next generation of engineers, like in their 40s, who's been practicing 20, 30 years, the body of knowledge, technical specialists across the world, you guys are making standards, And when you gave this presentation to us who aren't in this field, you couldn't help but start wondering how these next generation of engineers going to know how to make the decisions and choices that you're making right now. Do you feel
When I went to George Washington University, and that's a more academic geology department was there. And at the time, I was very frustrated with the knowledge I was getting because it seemed too theoretical. It wasn't practical. I was so frustrated, I organized and led my own field trip out to practical mining locations around. Years later, while I worked for Martin Marietta and worked for other companies, then I went to South Dakota for my master's, and that was a real practical type of education. And I specialized in materials. And I was happy, I was delighted with that. But 20 years after that, I've kind of found out that a lot of the concept on the training from GW has ultimately been more valuable to me in the longer term than the practical stuff.
Passing the baton to the 45-year-olds that's going to have to design and solve some of these problems across the United States, how do you feel your profession is doing teaching this next group of...
Poorly. My profession is doing poorly. A lot of geology departments are focused more on environmental work. I've had people come to interviews, even though the job description specifically says must have optical mineralogy in it. They don't have it. I've actually sent people away, sat down, and they haven't had any training in microscopy or anything like that. And I've told these young people, your time and my time is being wasted because I can't spend a year training you to do this work. I can't afford that. You have to get that in college and then come to me.
Are they teaching it?
They're not teaching it in some schools. They're teaching it in UGA. They're teaching it at Georgia Tech. But other schools are not teaching optical mineralogy or thin section microscopy at all. And that's leads to fewer employment opportunities for young geologists, really.
They aren't teaching anything but theoretical metallurgy either.
Yeah, there's all kind of things that are not being taught, and you know, a lot of this has to do too with, you know, we're talking about problem solving abilities and being able to just recognize something that's out of the ordinary with the material. Now I remember at GW, one of my, you have all kind of classes as geologists, one of which was in sedimentology. On our final, the guy had a piece of weathered brick. I was the only person that knew that this was a weathered brick. I was appalled at the time. I was happy that I got the credit, but I was appalled that these other people didn't know this. Why did I probably know that? Because my dad had me lay up brick and I worked construction, so I knew what all this stuff was. But other people don't walk around and look at buildings. My first wife, she was very upset because I would walk up to a building with my headlights and look at it. Very upsetting to women. Oh well.
Certain women, yes.
Stare at the wall. Yeah.
Not my current wife, but that's probably on tape and I'm going to get in trouble if she ever looks at it on YouTube, right? Oh well. People should be practical and they should know how they're living, what they're living in, where, you know, they don't necessarily have to know unless they're specialized where these materials come from, but you can't go and have a lot of complaints about something that you can't have this quarry or this pit in your backyard or 250 miles away when in fact when it then would come from would be from Australia or China or something like that.
It's very interesting. I recently was in Israel, and you go there to, for example, to Tel Aviv, and it's a city that's just under 100 years old, and pretty much none of the original buildings are still there because they were all built with local cement that was made from what essentially at one time was seashells. And it's all deteriorated, didn't have the strength. They thought it was great. And then you go a little over an hour away, you go to Jerusalem, and again, there's things that are over 2,000 years old. You can still see the walls. And what is that made out of? Limestone, which is well known, it doesn't last. But the climate is such that there's almost no rain there, so it doesn't weather like it would if you were to take some Jerusalem stone and bring it here. It probably wouldn't even last 2 decades here.
Yeah, you got
That you got to have good engineers who know what the local area is and what will last and what won't, where you're building.
I think we have to wrap up now. We've got at least one person saying us to wrap up, but not the guy who's in charge.
We hope you enjoyed this recorded presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.